Today's systems face the challenges of scale. A codebase today often consists of hundreds of thousands, sometimes even million lines of code, and the scale of that alone makes it pretty hard to reason about. In addition, today's systems are often developed by multiple different programmers organized into different teams. That means everyone gets their own view of how the system looks. No one has a holistic picture. So if we want to truly understand a large system in order to predict areas of high-risk changes, we need to somehow gather the collective intelligence of all those contributing programmers. This is a hard problem, but it's a problem that we can simplify somehow by understanding how code evolves. It turns out that code evolves to certain patterns, and it turns out that while all code is equal, some code is more equal than others. And to understand what I mean with this, let's take a different view of our codebase. Let's take an evolutionary view. Here's what that looks like. Please have a look at these graphs. All of them show the same thing. On the x-axis, you have each file in the system, and they are sorted according to their change frequencies. That is, how many changes or commits have you done to each file. And the number of commits is what you see on the y-axis. This chart presents the data from 3 radically different systems implemented in different technologies by different organizations, and we'll look at a different time frame. Yet they all show exactly the same pattern. They show a power law distribution. And this is something I've found in every single codebase that I've analyzed. And this is important because it gives us a tool to prioritize. Because in your typical codebase, most of your code will be in the long tail, which means it's rarely, if ever, touched. So we want to focus on the relatively small parts of the code where most of the development effort is located. So let's see how we can use Ampere Enterprise to help us out with the task. So this is the dashboard of the Ampere tool suite. It shows the analysis results on the open source project Mono. Mono is a compiler for .NET. And Mono is a huge project. It consists of almost 7 million lines of code. And now we will see how we can identify high-risk areas in Monos using something called a hotspot analysis. So this is what 7 million lines of code looks like. A hotspot analysis like this shows the folder structure of your codebase. So it's a hierarchical visualization where each large blue circle represents a folder in your codebase. And you use a hotspot analysis to identify complicated code that you also have to work with often. That is high-risk code. Here's an example on that. This is a package called MCS. MCS is a part of the core compiler. So let's click on that package and investigate its content. You see that each file in that folder is represented as a circle, and you see that the circles have different size. That's used to reflect the size of the underlying code, so the larger the circle, the more code. You also see that the circles have different color, and that's because the more red, the more opaque, the higher the change frequency of that code. Our number one hotspot here is called expression.cs, so let's click on that one and get a bit more information. You see that expression.cs has a really high change frequency. And this is important because change alone is one of the best predictors of software defects. And indeed, in my case studies, I find that hotspots are really good predictors of software defects. So a hotspot analysis is a tool to prioritize. The top hotspots only make up 3 to 6% of the total code, yet, in general, that relatively small part of the code tends to be responsible for the majority of all defects. And this is a huge topic, and this presentation has really just scratched the surface. If you want to learn more, please have a look at the book Your Code is a Crime Scene, or take a look at the online demo of the Ampere tool suite. In that online demo, you will see examples of both technical, social, and organizational analysis. Now, thanks a lot for listening to me, and may the code be with you. Thanks.